Alright, welcome back. And in this video, we're going to be taking a look at some more examples of using the double angle formula that we learned in the last video in how to solve some of these homework and test type problems. So let's take a look at some of these examples. So verification or proof problems. Verify that tangent of 3x is equal to 3 tangent x minus tangent cubed x all over 1 minus 3 tangent squared x. Now in this problem, I'd kind of alluded to this before. In general, when we're doing verification or proof problems, it usually works out a little bit better if we start with the more complicated side and work towards the simpler side. And now I did mention before there are some exceptions, and this is one of those exceptions. And the reason I say this is taking this quotient and putting it in a form that we can kind of compile it down into a tangent of 3x is going to be pretty difficult. Now we have the formulas, we would be able to do it that way, but it's going to be much more difficult. If we start with tangent of 3x and we use the formulas that we have to expand this out into tangent of single x's, we're going to find that it works a bit more cleanly. Now there's going to be a bit of algebra here, but we shouldn't have any problems. Now, as with all of the other examples I do in this video, or in all of my videos, I do highly recommend that you pause the video now, write down this problem, see if you can solve the problem on your own, and then after you get stuck or after you complete the problem, watch the video, see if the way I do it is the same way you do it, compare answers, and make sure that you got the correct solution. So let's go ahead and jump in. Tangent 3x. Now we don't have a triple angle formula. That's actually what this problem is asking us to derive. It's saying, well, we know what tangent of x is. We know a formula for tangent 2x. What's a formula for tangent of 3x? And turns out this right here is our formula for tangent of 3x. So we're really proving a new, what we could call a triple angle formula for tangent. Now we have a double angle formula, and we have an addition formula. So let's see if we can use both of those in tandem here. I can write tangent of 3x as tangent of x plus 2x. Can't I? Now x plus 2x, using the addition formula for tangent, this is going to be equal to tangent of x plus tangent of 2x all over 1 minus the product of these two. So 1 minus tangent of x tangent of 2x. All right, we're in good shape so far. So now that we're here, we can use the sum formula again for tangent for these two x's, but really we're calling that the double angle formula now, right? Instead of looking at this as tangent of x plus x, we can just directly apply our double angle formula. So in this numerator, I still have this tangent of x plus, now remember tangent of 2x is 2 tangent of x all over 1 minus tangent squared x. Right, this is our double angle formula, just a special case of our addition formula. So this is all over. Now we need to make that same substitution to this tangent 2x down here. So I'm going to have 1 minus tangent x multiplied by 2 tangent x all over 1 minus tangent squared x. Okay, so we have this quotient with fractions in the numerator and the denominator. So what we need to do next, we need to find common denominators for the numerator and common denominators for the denominator. Now it works out kind of nicely here because our common denominator for both numerator and denominator of the big fraction is going to be 1 minus tangent squared x. So once we find that common denominator in the numerator and denominator of the large quotient, we'll be able to cancel it out, right? And we'll see that happen here in a moment. So finding the common denominator here, we already found it's 1 minus tangent squared x. So I need to multiply this tangent x by 1 minus tangent squared x over 1 minus tangent squared x. And I'm going to get tangent x times 1 minus tangent squared x. I still have this plus 2 tangent x. This is going to be all over 1 minus tangent squared x And now this is our big fraction. Now in the denominator here, getting a common denominator, 1 is just 1 minus tangent squared over 1 minus tangent squared. So I have a 1 minus tangent squared x minus, and then this product here, 2 tangent x, or 2 tangent squared x. And this down here is all over 1 minus tangent squared x. Now I can cancel these 1 minus tangent squared x's. Again, if you don't see that right away, go ahead and multiply this top fraction by the reciprocal of this bottom fraction. You'll see that these 1 minus tangent squared x's cancel right away. And simplifying this out a bit, now in my numerator I just have what was in my numerator of the top fraction. So I have 2 tangent x plus a 1 tangent x, distributing this through. So that's 3 tangent x. And then I have a negative tangent squared times tangent. That's negative tangent cubed x. And in my denominator, I have 1 minus tangent squared minus tangent 2 squared. So this is a total of minus 3 tangent squared of x. And we're done. This is exactly what we want. This is our right-hand side in the problem. So now we've just derived a triple angle formula for tangent. Now I don't expect any of you to remember this. We'll probably never use it again. But it's kind of neat that we can now take what we've learned and derive all these new formulas, just like these classical ones that we've been using. Let's take a look at some more examples. Write sine of 2 tangent inverse x as an algebraic expression of x. So this is one of those evaluation problems, but now we're able to use the double angle formula. So remember, with an evaluation problem with mixed functions and inverse functions, we always want to make some substitution for what's in the argument of the outside function. So here I'm going to let my theta, say let theta equal tangent inverse x. Now we always just need the function. I'm not going to worry about this 2. Right? I'm not going to let theta equal 2 tangent inverse. The reason is that if I can make a triangle based on this theta, I can use my double angle formula for sine in order to solve the rest of the problem. And that's going to work out to be much easier than letting theta equal 2 tangent. Okay, so if theta equals 2 tangent, if theta equals tangent inverse of x, we know that by definition that means that tangent of theta is equal to x, and we also know that that theta is strictly between negative pi over 2 and pi over 2. So now we can make a triangle. Call this my theta. I have that tangent of theta equals x, so my opposite is x, my adjacent is 1, and my hypotenuse then is going to be the square root of 1 plus x squared. And now we're ready to go. My sine of 2 tangent inverse of x, with our substitution, this is the same as sine of 2 theta. And now we have our double angle formula. We know this is just 2 sine theta cosine theta. And now we can plug in from our triangle. For my triangle, I see that my sine is opposite over hypotenuse, or x over the square root of 1 plus x squared. And my cosine is adjacent over my hypotenuse, or 1 over the square root of 1 plus x squared. So multiplying this out, I'm going to have 2x on the top, and on the bottom, these square roots cancel with each other, and I just have 1 plus x squared. All right, and we're done. We've successfully written sine of 2 tangent inverse x as an algebraic expression of x. Okay, now let's take one with some numbers. Let's say we want to solve a problem like this exactly. So find the exact value of sine 2 cosine inverse of 7 over 25. So again, we're going to make a substitution. we're going to let our theta be the inverse function cosine inverse of 7 over 25. So then by definition, I know that cosine of theta is equal to 7 over 25. And I also know that theta is between 0 and pi. Now this gives me some good information here. If theta is between 0 and pi, that means that my sine of theta is positive. And our cosine of theta obviously is positive because it's given to us right here. So let's take a look at our triangle. We have that cosine of theta is 7 over 25, so that's my adjacent over my hypotenuse. And we need to find this other side, so let's do it down here. We'll call it A. We know that 7 squared plus A squared is 25. So then 25 squared. So then A is equal to the square root of 25 squared minus 7 squared, which is equal to the square root of 625 minus 49. This gives us the square root of 576, which turns out to be exactly 24. So we have this A equals 24. All right, now we're ready to go ahead and solve the problem. Sine of 2 cosine inverse of 7 over 25. By our substitution, this is just sine of 2 theta, which we know is 2 sine theta cosine theta. Now plugging in, I know that my sine theta, looking over here, is going to be 24 over 25. So I have 2 times 24 over 25. And our cosine theta, we know, is 7 over 25. Multiplying this out, we have 2 times 7 times 24, which is 336, all over 625. And this does not reduce at all because the only factors of 625 are multiples of 5, and there is no 5 as a factor of my numerator. So we're as done as it gets. All right, I hope these examples help. And in the next video, we're going to be looking at a new set of trigonometric identities. We'll see you there.